Hello viewers, welcome to the lecture on feedback control. In this lecture we will continue with the concept of feedback control which was discussed in the previous lecture. Now I will demonstrate the computation of feedback control using an example. So first let us summarize the concept of feedback control which was seen in the last lecture. So let x dot equal to Ax plus Bu be a control system given to us where A is n cross n matrix and B is a column vector n cross 1 matrix. Now let U the control is a feedback control of the form Kx, where K is a unknown column K is a unknown row vector, and so when we substitute the control in this equation we will get Ax plus Bkx, so that will finally become A plus Bk of x. So let S be a set mu1, mu2 etc. mu n be an arbitrary set of numbers. So n numbers are given arbitrarily. So now the question is it possible to find the matrix K such that the eigenvalues of A plus Bk are exactly the set S mu I, where I is equal to 1, 2, 3 up to n. So is it possible to find a K in this manner? So the answer is we can find, provided the system is controllable. So let us call this system equation as 1 if the system 1 is controllable, or the rank of B, AB, A square B etc. A minus 1 B. If the rank is n, then we can find a K like this. So if you are able to find how to find this K, that is for this we follow this procedure. The procedure is earlier we studied that there exists, because the system is controllable, there exists a non-singular matrix T such that T A T inverse is in the companion form 0 1 0 0, last is 1, and then minus alpha n etc. minus alpha 1, and T into B is 0 0 1. This is the D matrix. So we can find a unique non-singular matrix T so that this happens, isn't it? So here you can easily see that alpha 1, alpha 2, alpha n, these are the coefficient of the characteristic equation, characteristic polynomial of the matrix C. In other words, it is the coefficient of characteristic polynomial of matrix A because A and C are similar matrices, they will have the same eigenvalue. So, characteristic polynomial is the same for both of them. So, the coefficient of characteristic is the last row of the matrix C. Now, we are interested in A plus Bk. We want that the eigenvalues of A plus Bk are mu 1, mu 2, mu n. So, we can write this as A is T inverse C T and B is T inverse D. Okay. So, we can write this as T inverse T B. So, this can be written as T inverse T B, B can be written like this, then we have K, then T inverse T, it can be written like this. So, that the final thing is we can take T inverse outside the left side and T can be taken out in the right side. So, the remaining things are C plus T B equal to D and then K into T inverse. So, this expression is there. So, it is easy to see here A plus Bk and C plus Dk T inverse, these are the similar matrices. So, the eigenvalues of C plus Dk T inverse and A plus Bk are same. So, now if you calculate this, therefore, the last column, last row which will appear in this matrix should be the characteristic coefficient of the characteristic polynomial of A plus Bk. So, that is the meaning of this expression. Now, if you calculate C plus Dk T inverse, so C is 0 1 0 0 etc. minus alpha n minus alpha 1 and D is 0 0 1 and K is Kn minus 1 K1 into T inverse. So, this will appear like this plus the product of these two, it will be 0 0 etc. K n K1 into T inverse. Further, if we calculate, we will get this expression to be the first matrix is C plus the second one is 0 0 first n minus 1 column. The last column we will multiply this row with this T inverse matrix, we will get gamma n minus 1 gamma 1. So, adding these two matrices, finally, we will get the matrix to be 0 1 0 0 0 0 1 and then we will get minus alpha n plus gamma n and minus alpha 1 plus gamma 1. So, this should be the coefficient of the polynomial. So, the characteristic equation of A plus Bk, what is required is lambda minus mu 1, lambda minus mu 2, lambda minus mu n equal to 0. So, this will be some polynomial like this plus beta n equal to 0. So, what we have is the last column of this matrix, last row of this matrix should be minus beta n minus beta n minus 1 etc. So, this implies that minus alpha I plus gamma I, that should be equal to minus beta I is equal to 1 to up to n, or we want to calculate this gamma I, that is equal to alpha I minus beta I. So, minus beta I equal to 1 to n, and the previous slide we have seen the relation here, this expression we want the K matrix only, but what we have calculated is this expression. So, the relation between K matrix and this gamma Kn minus 1 K1, that is the last row, and this last row is gamma n etc. So, the relation between these two is this K multiplied by T inverse is given by this gamma matrix. So, from the previous page we know that Kn minus 1 K1 into T inverse, that is gamma n minus 1 into gamma 1 up to that. So, this implies the K matrix is gamma matrix multiplied by T. So, if we use this K matrix as the feedback matrix here, this one K u equal to Kx, we will get mu 1, mu 2, mu n as the eigenvalue of the matrix A plus Bk. So, that is what we will see the computation as an example we will see here. So, if you consider the matrix A to be say 1 2 2 1 and the matrix B as 2 1, okay, and let S be the matrix, the set minus 2 and 1. So, the question is, so is it possible to find a matrix K which is called K2 K1 such that A plus Bk has eigenvalues minus 2 and 1, the arbitrarily given set are minus 2 1 here. So, is it possible to find K? Now, we can first check whether the system is controllable or not. So, the system is controllable. So, the set U, the matrix U is B is 2 1 and AB is 4 and 5 if you compute this one. So, this implies the rank of U is 2, therefore, it implies the controllability. So, according to the principle which we have seen earlier, we have to find the matrix T. So, we have to find the matrix T first. So, T is the first row is alpha, the second row is alpha into A, where the companion form we have studied that the alpha matrix can be computed by using 0 1 and U inverse. Okay. So, this implies alpha is equal to 0 1, U is this matrix and U inverse if you calculate, that is 5 by 6 minus 4 by 6 and minus 1 by 6, 2 by 6. Okay. So, if you multiply this two, we will get the alpha value to be minus 1 by 6 and 2 by 6 as the alpha value. The second row of T is alpha into A, alpha into A. So, this is alpha and A matrix is there. If you calculate this one, we will get 3 by 6 and 0. Okay. So, this implies the T matrix is minus 1 by 6 and 2 by 6, 3 by 6, 0. So, T matrix is obtained. Then it is clear that T A T inverse will be equal to C. So, here C is nothing but the companion form, and the last row of this will be having the coefficient of the characteristic polynomial of the matrix A. Okay. So, we will get the matrix C to be, because if you see A, the eigenvalues of A matrix can be calculated, and from there we can calculate, or directly we can calculate the characteristic polynomial, that is lambda square minus 2 lambda minus 3 equal to 0. So, the last row of C will be 3 and 2. Okay. Is the C matrix, and T B we can easily check, it will come out to be 0 1 here. Okay. So, we got the T matrix and C D matrix, etc., all these are available. Now, to find the K matrix, which is K2 K1, we have to follow the procedure that we have to follow that K2 K1, it is equal to gamma 2 gamma 1 multiplied by the T matrix. K matrix equal to gamma into T, gamma 2 gamma 1 into T matrix, and gamma values are obtained by alpha I minus beta I. Now, we have to see what should be the value of beta I. Beta I are calculated by the characteristic equation of A plus Bk. It is given by, because we require the set minus 2 and 1 are the eigenvalues. So, the characteristic equation can be calculated as lambda plus 2 into lambda minus 1 equal to 0. So, this implies lambda square plus lambda minus 2 equal to 0. So, beta 1 is 1 here and beta 2 is minus 2. Therefore, we get the value gamma 1 is alpha 1 minus beta 1, which is equal to alpha 1 is here minus 2 and beta 1 is 1 here. So, the value is 3. Gamma 2 is alpha 2 minus beta 2, alpha 2 is minus 3 and minus beta 2 is plus 2 equal to minus 1. So, we got the value of gamma, and gamma multiplied by T matrix K2 K1, that is equal to gamma 2, that is minus 1 minus 3 multiplied by the T matrix minus 1 by 6, 2 by 6, 3 by 6, 0. So, by multiplying this 2 we will get the value K matrix is gamma 2 gamma 1 into T. So, we will get the value minus, that is plus 1 by 6 minus 9 by 6 minus 8 by 6 and minus 2 by 6, that is the value of the matrix K. So, the feedback control U of t is given by minus 8 by 6 minus 2 by 6 into the x1 x2 are the solution of the problem, the given control system. So, that is nothing but minus 8 by 6 x1 minus 2 by 6 x2 is the feedback control of the problem, and substituting this control for finding the control we have to find x1 x2, but in real life situation at each instant of time we can measure the x1 and x2 value, the position the current position of the dynamical system can be measured at each instant of time. So, depending on those values the control should be applied on the system. So, so that it proceeds, the control is working on the system and it will drive the system as we desired, because the eigen value are selected for a particular purpose. In this case, just to demonstrate the problem we have taken minus 2 and 1. So, it may not serve any physical purpose of any particular problem, but normally this procedure is applied for stabilizing a system. If you have a control system x dot equal to Ax plus Bu, to make the system stable, the eigenvalues of the A plus Bk matrix, it should be negative, that is for asymptotically stable condition we need that the eigenvalue of the matrix A plus Bk, all of them should be having negative real part. So, if we select the set S in such a way that all the eigenvalues have negative real part and then find the feedback control, then we are sure that the system becomes asymptotically stable. So, that is the purpose of this particular result. That is the main purpose for stabilizing a control system. So, in this lecture we have seen a demonstration of how to find the feedback control for the system where A is a n cross n matrix, but B is a column n cross 1 matrix. But the general case is we have to do a similar work for the general system where A is n cross n and B is a n cross m matrix. So, in this case how to find a feedback control. So, here we want to find a feedback control U equal to k times x. Same procedure, but only difference is k is here So, we want to find a feedback control U equal to kx in such a way that A plus B into k has desired eigenvalues. So, this is so far we have seen the method of finding the feedback control for the system in which the matrix B is n cross 1, that is a column vector matrix. And the next lecture we will consider the system x dot equal to A x plus B u, in which B is a general n cross m matrix. So, we want to find a feedback control u equal to k x, where k is a n cross m matrix, so that A plus B k has desired set of eigenvalues. Okay, thank you.